Every so often, a star in the sky suddenly becomes brighter, sometimes brighter than an entire galaxy. For weeks or months, it outshines everything around it. Then it fades, leaving behind either a tiny dense core or nothing at all. This is a supernova. It is the most violent, most energetic event in the universe since the Big Bang. And it is the source of almost everything we are made of. Supernovae are not just cosmic spectacles. They are the forges where heavy elements are created. The iron in your blood, the calcium in your bones, the gold in your jewelry, all were made in supernova explosions. Without supernovae, there would be no rocky planets, no life, no us. Today, we're going to explore these stellar cataclysms, how they happen, what they leave behind, and why they are essential to the universe. Two paths to destruction. There are two main types of supernovae, and they happen in very different ways. Type 1, specifically Type 1a, occurs in binary star systems where a white dwarf steals mass from a companion star. When the white dwarf reaches the Chandrasekhar limit, about 1.4 times the mass of the Sun, it can no longer support itself. It collapses and ignites a runaway thermonuclear explosion, completely destroying the star. Type 2, core collapse supernovae, happen to massive stars, those with at least 8 times the mass of the Sun. These stars burn through their fuel quickly, creating an onion-like layered structure. When the iron core can no longer produce energy, it collapses in less than a second, triggering a shock wave that blasts the outer layers into space. The core becomes either a neutron star or a black hole. A countdown to explosion. Stars like the Sun live for billions of years, but massive stars live fast and die young. A star 20 times the mass of the Sun might live only 10 million years. It fuses hydrogen into helium, then helium into carbon, then carbon into neon, then oxygen, then silicon. Each stage is shorter than the last. The final stage, fusing silicon into iron, lasts only about a day. Iron is the end of the line. Fusing iron does not release energy, it consumes energy. So the star's core has no more fuel. Without fusion to support it against gravity, the core collapses. In less than 1 second, a core the size of Earth collapses into a neutron star just 20 kilometers across. The infalling outer layers bounce off this new, hard core, creating a shock wave that blasts the star apart. White dwarf goes boom. Type 1a supernovae are completely different. They occur in binary systems where one star is a white dwarf. The white dwarf pulls gas from its companion. Over time, it gains mass. When it reaches the Chandrasekhar limit of 1.4 solar masses, the pressure and temperature in its core become high enough to ignite carbon fusion. But unlike in a normal star, this fusion is uncontrolled. The entire white dwarf explodes in a thermonuclear fireball. Nothing remains. No neutron star, no black hole, just an expanding cloud of debris. Because Type 1a supernovae always happen at the same mass, they have roughly the same peak brightness. This makes them excellent standard candles for measuring cosmic distances. Observations of Type 1. A supernovae led to the discovery that the universe's expansion is accelerating, a discovery that won the Nobel Prize in 2011. What a supernova looks like. When a supernova explodes, its brightness increases dramatically over a few days. At peak, a single supernova can outshine an entire galaxy of 100 billion stars. The explosion ejects material at speeds of 10,000 to 30,000 kilometers per second, up to 10% of the speed of light. The expanding debris creates a glowing nebula called a supernova remnant, which can remain visible for thousands of years. The most famous supernova remnant is the Crab Nebula, created by an explosion observed by Chinese astronomers in 1054 AD. At its center is a pulsar, a rapidly spinning neutron star. In 1987, a supernova in the Large Magellanic Cloud, SN 1987A, was close enough to study in detail. It was the brightest supernova seen from Earth in 400 years, and it gave astronomers a wealth of data about how these explosions work. Neutron stars and black holes. What is left after a supernova depends on the mass of the original star. For stars between about 8 and 20 solar masses, the core collapses into a neutron star, an incredibly dense ball of neutrons, just 20 kilometers across, but with the mass of a star. For stars above about 20 solar masses, the core collapses all the way into a black hole. In both cases, the explosion blasts most of the star's mass into space. This enriched gas will eventually mix with the interstellar medium, becoming the raw material for new stars, new planets, and new life. Every supernova scatters heavy elements: oxygen, carbon, silicon, iron, gold, uranium, across the galaxy. We are made of stardust, literally. Supernovae and life. The connection between supernovae and life is direct. The Big Bang produced only hydrogen, helium, and traces of lithium. All heavier elements were forged inside stars, but those elements stayed locked inside the stars until the stars exploded. Supernovae are the only way that elements like carbon, oxygen, and iron get spread through the galaxy. When our solar system formed 4.6 billion years ago, it contained heavy elements from countless previous supernova. Those elements became Earth and then became us. A supernova may also have triggered the formation of the solar system. A shockwave from a nearby explosion could have compressed a cloud of gas and dust, causing it to collapse into the sun and planets. Some scientists even suggest that supernovae may have caused mass extinctions on Earth through radiation or climate effects. Catching the action. Supernovae are rare. In a galaxy like the Milky Way, only about 1 or 2 explode per century. The last observed supernova in our galaxy was in 1604, before the invention of the telescope. But with modern telescopes, we see supernovae in other galaxies all the time, dozens per year. Automated surveys like the Zwicky Transient Facility and the upcoming Vera Rubin Observatory detect them within hours of explosion. Neutrino detectors and gravitational wave observatories can also detect supernovae. In 1987, neutrinos from SN 1987A were detected on Earth hours before the light arrived. This was the birth of neutrino astronomy. In the future, we may detect gravitational waves from nearby core collapse supernova, giving us a new way to probe the inner workings of these explosions. The cycle of life and death. Supernovae are endings and beginnings. They mark the death of a star, but also the birth of new worlds. They are the universe's recycling system, taking the ashes of dead stars and turning them into planets, plants, and people. Every time you look at a piece of gold, every time you feel the iron in your blood, you are seeing the aftermath of a supernova. We owe our existence to these cosmic explosions. They are violent, destructive, and beautiful, and they remind us that we are not separate from the universe. We are part of it, made of the same stardust that fills the galaxies. The next time you look up at the night sky, remember that somewhere, a star is exploding, seeding the future with the elements of life. What do you think? Would you want to witness a supernova up close? Or is it better to admire them from a safe distance? Let me know in the comments. Thanks for watching Daily Dose of Space. Stay curious, and I'll see you tomorrow.